Alright, the last thing we're going to talk about with calculation of enthalpy or delta H values is looking at estimation of delta H based on bond energy. How much energy is needed to break a bond, how much energy is released when bonds are formed. Whenever we turn reactants into products, this idea of breaking bonds and forming new bonds becomes very important, because we are breaking apart the bonds of the reactants, rearranging the atoms, and then creating new bonds for our products. So how much energy is necessary for that? We can find the approximate bond energy values given in several tables. So this picture shows you some examples of bond energy associated with each type of bond. Now, bond energy differs based on whether we have single, double, or triple bonds, even between the same atoms. So we see here carbon-carbon single bond has less energy than a double bond, less energy than a triple bond. So as our bond order increases, the energy needed to break those bonds also increases. All right. We also see a difference even between different atoms, so carbon-oxygen double versus carbon-oxygen triple. Again, bond order increasing, we see an increase in energy requirement. There's also some difference in bond energy based on how close together the atoms can get. Remember, that is based on the size or radius of the atoms when they come together. The larger the atom size, the longer that bond needs to be. The longer the bond, the less energy, so the weaker it is. So if we look at carbon iodine, iodine is huge, so this bond between carbon and iodine has to be very long, so it's fairly weak. When we compare that to carbon fluorine, fluorine's in the same family as iodine, but fluorine is much smaller, the bond is much shorter, the two atoms can get closer together, we have more energy requirement to break it up. Alright, so we need to look at bond strength in terms of the length of the bond. The longer the bond is, the weaker it gets. And bond order. The more electrons being shared between two atoms, the more energy needed to separate those two atoms. Alright, so these are referred to as bond energies or bond dissociation energies. So you'll see that written as BDE frequently, so bond dissociation energy or bond energy. All right, and we measure these in energy units, kilojoules per mole. Now these values we see on tables are actually approximations or averages when we look at the energy requirements to break a bond, looking at the same type of bond in multiple molecules or in multiple conditions. So for example, we have methane. Methane has 4 CH bonds. And we think of all 4 of those bonds as being identical. But once we start breaking those bonds, once I start breaking one of the CH bonds, the other 3 bonds are no longer in an identical environment anymore. So we see the bond energies change. So the energy required to break the first bond, 435, but then the energy required to break the second bond after the first one's been broken is a little bit higher. Right? Energy required to break the third bond drops down, and then energy required to break the last one is very low. We take the average of those 4 values to get the value that we would call the CH BDE or bond dissociation energy. Alright, so it is an average value, but it's a good approximation. So using bond energies to calculate delta H is really an estimate or an approximation and not going to be as accurate as doing experimental calorimetry tests or even using Hess's law or heats of formation. But it can be used to give a good estimate. Now these values also can be determined based on this idea of potential energy. If we imagine 2 atoms that are going to be bonded together, they have to be the correct distance apart based on their radii, to form the appropriately strength bond to make it stable. So in this graph, what we're looking at is measuring the potential energy within the bond versus how far apart the atoms are that are participating in the bond. So if we start with 0 distance apart, so essentially the two atoms, if they could be occupying exactly the same space, which is not possible, so that's why you see the potential energy going off toward infinity up here. But as soon as we start moving them apart, far off of each other, we see that potential energy drop, okay, as they start getting further and further apart. And then we see it dip down to the minimum. Okay, at this minimum, that is the optimal distance the two atoms are apart to form the stable bond. If we start pulling the atoms apart further than that, we start seeing the potential energy increase. Alright, so potential energy starts increasing as they get further and further apart, but it's approaching 0. So once the atoms are so far apart, they're not interacting any longer, then it is going to 0. Okay, now the atoms are so far apart, they're not forming a bond, they're not interacting at all, they're just two separate atoms. So our potential energy is 0. Now the energy we say that is involved in the bond occurs at this minimum right here. So this one is negative 436 kilojoules per mole. So potential energy is negative because that is the energy released when the bond is formed. And that is the minimum when we look at this separation of the atoms to define the optimal distance. Alright, so if we look at any type of reaction, if we can look at the bond association energies that are involved in the reactants, those bonds have to be broken, and then look at the bonds that we have to form for the products, we can get an estimation of the energy requirements for the reaction or process. So if we're looking at two water molecules breaking down into 2H2 and O2, down here I've drawn out what these structures look like. So here's one water molecule, here's the second one, right, because we have a coefficient of 2, so we need to pay attention to that. And then on the product side, I'm going to be forming one H2 molecule. Here's the second one, because again, coefficient of 2. And then one O2 molecule. So for this, notice it's important that you know what the structure looks like. You know whether it's single bonds, double bonds, triple bonds. You know what atoms are bonded to one another. So this is going to rely on your Lewis structure skills. We're going to only be looking at small molecules, so nothing huge and weird, but you need to be able to find Lewis structures for these small molecules so you know what atoms are bonded to what. So I don't want anyone going, oh, H2O looks like this. No, it does not, right? Make sure you know your Lewis structures. Right, once we have that, then we know that we have to break all 4 of these OH bonds. So here's our 2 water molecules. We got to break all 4 of these. So I have 4 OH bonds. We are forming 2 H2 bonds. Alright, so these 2 are being formed. And then we have one OO double bond that also needs to be formed. Alright, so we're going to calculate all of the energy requirements for breaking the 4 bonds. So 4 times, here's our OH bond dissociation energy. This gives us our energy needed to break. So energy going in, this is our endothermic requirement, the energy we have to put in. Now for forming bonds, we have 2 HH bonds, so that's this one, and we have one OO double bond. Alright, so when we add up all of those values, here is our exothermic release. So this is the energy that comes out from forming those bonds. So we have 1836 is the energy required to break everything, so we're going to absorb that much energy. Then we're going to release the 1370 when the new bonds are formed. So we're going to put these numbers together. So our 1836 was a positive number, endothermic. Our 1370 is an exothermic number, so that's where we have the negative. So we end up subtracting. So we get 466 kilojoules of energy remaining, and that is positive. So we have more energy that goes in than is released. So overall, this would be an endothermic reaction. Here's another example where we can see in a diagram form what's actually happening. So starting out with our H2 and our F2. Alright, so here's our H2, here's our F2. We have to break the HH bond and the FF bond. So here we've put the energy in order to break it. So endo going up. Here's our isolated atoms after we've broken everything. And now we're going to rearrange to form the products. So we're going to put our H and our F's together. So when we do that, energy is going to be released. And then here we have our difference. Because the difference is negative now, we have an overall exothermic reaction. And so we see that listed up here. The 546 is on the product side, so it's exothermic. So this leads us to our equation. The delta H of the reaction, or close approximation, is equal to the summation of the bond energies that must be broken, so on the reactant side, minus the bond energies that are formed. Alright, and if we have a positive value, it's an overall endothermic process, and if we have a negative value, it's an exothermic process. Alright, so we're going to calculate what we have based on our bond energies. So H2S, and then we have F2, SF4, this F4, and then HF. Alright, so we can draw all of our Lewis structures. Now we want to start assigning. So under the breaking category, breaking bonds, I need to break 2 of my HS bonds. So that's these two. I need to break 3 of my FF bonds because I have a coefficient of 3, breaking all of those. Alright, so that means that I have 2 times 347 and 3 times 154. Alright, so if I put all that together, I can look at the energy required to break those bonds. So I get 1156. And now we're going to look at forming. And I want to form 4 SF bonds and 2 HF bonds. Alright, so I have 4 times 327 and 2 times 565. So over here I have 2,438 for the energy released when the bonds are formed. So when I put those together, my delta H will be 1156 minus the 2,438. So more energy is released than goes in, and I get negative 1,282 kilojoules. Alright, so that's based on bond energies. Alright, let's try one more. I'm going to draw my structures up here. So I have NH3, and O2, NO2, and water molecules. Alright. Now with this one, you may notice that NO2 has resonance structures. Alright, so I could have just as easily drawn NO2 like this. Alright, because of the double bond, it can be in either position, so we have resonance. So you might even draw the composite form of that. So how do we treat that with bond energies? Alright, one way we can do it is just treat it like it has one double bond and one single bond and move on with our day. Other people like to look at it in terms of averaging. So instead of having a bond order of 2 and a bond order of 1, we're going to average. We're going to have a bond order of 1/2, or sorry, 1.5. Alright, so either way you want to do it, you're actually going to end up with the same number. So it doesn't matter a whole lot. Alright, so let's look at what we have to do for breaking. So for breaking, I have 3 NH bonds per molecule, and I have 4 of them. So we're actually going to need 12 NH bonds broken. I have 7 for a coefficient for O2. So I have 7 of those to break. Alright, so I'll write that down here. So NH3 is 389. And our O2 is 498. Alright, so that gives us 8,154 for the energy required to break the bonds. Now for forming, I'm going to treat it as a double bond and a single bond, so I have 4 of the NO double bonds and 4 of the NO single bonds. And then I also have 12 of the OH bonds, because I have 6 water molecules that have 2 of those bonds each. So 4 times 590 and 4 times 222 and 12 times 464. I'm going to add all that together and I get 8,816. Alright, so remember for our delta H, we're going to do 8,154 for the energy going in minus 8,816 for the energy going out. And overall, this gives us negative 662 kilojoules. So again, exothermic. Alright, so make sure you can draw the Lewis structures. Make sure you can count what kind of bonds you have, single, double, or triple. Make sure you're accounting for everything. If you have to, draw the picture and start crossing out the bonds so you don't leave anything out. Alright, so here's our summary. In order to break a bond, you have to put energy in. So every reaction starts with putting energy into the reaction to break all of those bonds. Once all the bonds are broken, then you can rearrange the atoms, and any new bonds means that energy is being released. Alright, so forming new bonds is an exothermic process. We can determine the strength of the bonds based on table values. From the table values, we add up all the energy required to break the bonds, and then subtract all the energy that is formed or energy that is released when the new bonds are formed. Alright, so if we think about using this idea with bond energies, we can also apply this to ionic compounds. Of course, bond energy associated with the ionic compounds is called lattice energy, which hopefully you remember talking about from 1211. Lattice energy is the energy that is released when we have our positive and negative ions interacting in a lattice. So just to remind you, if we put our Na, sodium, with our chlorine, we're transferring electrons from the sodium to the chlorine to create ions. Once the two ions come together in a lattice structure, energy is released. Alright, this energy that is released is called the lattice energy when we're looking at gaseous ions coming together to form the solid. And lattice energy is given by this equation down here. And it depends on two basic properties of the compound, or the atoms coming together. The first is going to be the charges. So these Q values here represent the charges on the cation and anion. So whether that's +1, +2, -1, -2, etc. These are the charges. The bottom number down here is going to be the distance between the ions. All right, how far apart they have to be. The closer they are together, the greater the lattice energy. The higher the charges, the greater the lattice energy. All right, so here's our summary for that. Based on our two properties, as the charges increase, so +1 -1, +2 -2, or +3 -3, as the charges increase, either both or separately, the attraction increases, and therefore the lattice energy increases. So the top of our fraction over here gets larger, the energy gets larger. All right. Attraction also increases as the atoms are able to get closer together. They can get closer together when they have smaller radii. So the smaller the radii of the ions, the closer they get together, the greater the lattice energy. So on our fraction over here, the smaller this bottom part is, the larger the energy is. So these graphs show you that same kind of concept. When we go NaF, NaCl, NaBr, Nai, sodium stays the same, but we're increasing the radius of the anion, so the bond is further and further apart, the distance between them grows, we see a decrease in the lattice energy. All right? It's not a huge decrease, but it is there. We see a much larger effect based on the charges. As we go from a +1 -1 with sodium chloride to a +2 -2 with magnesium oxide, we see a huge jump in lattice energy. So charge plays a greater role in lattice energy compared to the size and the distance between the ions, but we can look at both characteristics to determine relative lattice energy values. And this table gives you some estimations on the lattice energy. So smaller ions are going to have a higher value. As the ions get larger and the charges stay the same, the values decrease. All right, and that's true regardless of what type of ion you're looking at. Once you switch to a +2 ion, our values dramatically increase. All right, increasing that charge increases the lattice energy, and increasing to a -2 ion, it jumps even higher. All right. So lattice energy is one of the values we can use when we're looking at finding delta H values based on this Hess's law idea. So remember Hess's law, we want to use multiple reactions to try to find a delta H value for a desired reaction. So we can look at all of these energy equations, and lattice energy is just one of those. So for example, if I want to look at the heat of formation value for sodium chloride, here's my reaction, starting with elemental sodium, which is solid, and half of the Cl2, which is in the gas phase. How do I make sodium chloride solid? What is the heat of formation? So I'm going to imagine starting with sodium solid. First thing I need to do if I'm going to get it to interact with chlorine is I have to turn the solid into a gas. Only gaseous ions can lose their electrons. So my first step here is actually sublimation, which is a phase change from solid to gas. So this is the energy required to turn the solid into the gas. Once it's in the gas phase, now I need to take an electron away from it. Hopefully you remember this, first ionization energy. So first ionization energy of sodium to form the ion. We have our delta H value. Now let's look at the chlorine. I have 1/2 of a Cl2. I need to break apart the Cl2 molecule, so I need to break that bond. And remember, we just looked at that. Bond dissociation energy is the energy needed to break that Cl-Cl bond. But I only need half of it because of this. Alright, so here's half of that bond dissociation energy. And now I have a single chlorine atom. I need to add an electron to it to make it an anion. So remember that. It's called electron affinity. So adding an electron. So here that value is. And remember, these are negative values. So that's an exothermic reaction or process. Alright, so now I have Na plus in the gas phase. I now have Cl minus in the gas phase. So I'm putting those two together to create the solid. This is the definition of lattice energy. So here's our value. So lattice energy is one of these reactions that we would need in order to calculate my delta H formation. So now I'm going to add up all of these steps that I took in order to form my heat of formation value. So starting with the Na solid, starting with half the Cl2 gas, making the sodium chloride, required all of these steps. So I'm going to add them all up, including the negative ones, to give me my heat of formation value for sodium chloride. And notice it is negative, as most of them are. The Born-Haber cycle is a way of determining the lattice energy values based on many of those equations that we just looked at, but also including heat of formation values to find lattice energy instead of using lattice energy to find heat of formation. So this is the same compound. We're still looking at NaCl, and we're going to start here. Alright, so here's our elemental sodium. Here's our 1/2 of our elemental chlorine. We're doing the same step. So the first step, turn the solid into a gas. So here's sublimation. Second step, ionize the sodium. Alright, so this is the ionization energy. Alright, then next step, break up the chlorine-chlorine bond. So that's 1/2 of the BDE, bond dissociation energy. So now I have my cation, I have my chlorine atom by itself. Now I need to add an electron to it. So this is electron affinity. Alright, and remember it's negative, so now we're going the other way. Now we have both of our ions, and we're trying to put those together to make the solid. So that's this long arm here, and that's going to be our lattice energy. So one last part that we didn't have before, but now we do, is our heat of formation value. Starting with the elements and going to the ion, this is our heat of formation. Alright, so now putting all of this together. So I'm going to add up my 107, my 496, my 122, so moving up. And then I'm also going to add this 411. Alright, so that covers this entire distance. I'm going to subtract the 349 because it's going part way down, and that's going to give me this part. Alright, so if we think of this whole distance here as x, we think of this distance here as y, and we'll think of this distance as z. X is equal to y plus z, right? So I'm going to add up everything on x. I'm going to subtract y, and that should give me z. Alright, and that's going to be 787, which is our lattice energy. This is kilojoules. Alright, so let's look at the Born-Haber cycle for calcium fluoride. Same ideas, same setup. This is where we're starting. Alright, we are starting with calcium, elemental. We're starting with our fluorine. And, yep, okay, this is gas. Alright, so first thing we want to do, we have to ionize calcium. So we're going to take our first ionization energy, I'll call it first, and that's written down here, so that's 590. And because calcium goes to a +2 and not a +1, I also need my second ionization energy, which is also listed as 1150. So all of that is needed in order to ionize. Oh, we missed our first step, our sublimation. So I'm going to go back. Alright, I need to turn this into a gas. So sublimation energy is given. They call it atomization. It's the same idea. So this is 179 right here. We have the two ionization energies together for this next step. Now we have calcium as a +2. We still have F2. And our next thing is we need to be able to break up the F2. Alright, so I need 2 Fs. In order to break up the F2, bond dissociation energy. So that's the 158. Alright, and then of course the next thing, we need to add those 2 electrons that we took from calcium and put them on the fluorines. Alright, so electron affinity. And we have -348. So here's our -348, but I'm going to multiply by 2 because I got to do it twice. Alright, so that gives me calcium 2+ and 2F-. Alright, and remember I'm trying to get down here to make calcium fluoride. So here would be my lattice energy that I'm looking for. And so this last part that we need to fill in is the heat of formation. Starting with the elements and turning it into the compound. So the heat of formation value, the last one down there, -1220. Alright, so now if we're going to figure out what we have, we need to add everything together. So we're going to add everything on this left side. So I have my 158 at the top, my 1150 and 590 for the ionizations, my 179 for the sublimation, and we're going to also add the 1220. Alright, and then on the other side, we're going to subtract 348 times 2, and that should give us our lattice energy. I believe this gives us 2601. Alright, and here is all that written out for you again. So we started here, our elemental forms, sublimation of the calcium to make gas, 2 ionization energies to take 2 electrons away to form the cation. Then we had to break apart the FF bond, so bond dissociation energy. Then we're going to add the 2 electrons back, so electron affinity times 2 to get our ions. And then our last step over here, our heat of formation value, is needed to calculate the lattice energy. So adding up everything on the left side column and subtracting 2 times the 348 gives us the 2601 kilojoules for our lattice energy. And how to fill